welcome back. Today we are starting with Applied Physics Part 2, where we will look at diffraction. We will be looking at these topics in our video. Let's start with our first topic, diffraction. Diffraction is the bending and spreading of light waves when they encounter an obstacle or pass through a small opening, aperture. It is one of the key phenomena demonstrating the wave nature of light. Diffraction becomes noticeable when the size of the obstacle or aperture is comparable to the wavelength of the light. Key characteristics of diffraction are wave bending and interference and diffraction patterns. You can just read out details about them in this slide. There are two types of diffraction. Fresnel diffraction that occurs when the source of light and the screen, or observing surface, are relatively close to the aperture or obstacle. In this case, the light waves are spherical or curved, and the diffraction pattern varies with distance. Fraunhofer diffraction that occurs when the light source and the screen are far from the aperture, and the waves are essentially plane waves. The diffraction pattern is simpler and more stable. The diagram for diffraction typically show a light wave approaching an aperture or obstacle, with the wave front bending as it passes through or around the object. The diffraction pattern on a screen or surface will display alternating bright and dark regions due to constructive and destructive interference of the diffracted waves. Fresnel diffraction occurs when light waves diffract around an obstacle or through an aperture in situations where the source and the screen are at a finite distance from the aperture. The wavefronts in Fresnel diffraction are not flat but rather spherical or cylindrical, depending on the shape of the wavefront and the distance from the source. Key points include near-field diffraction, curved wavefronts, and detailed pattern. Fresnel diffraction occurs when the following condition is met. Fresnel number, F equals alpha squared divided by L lambda, which is greater than 1, where alpha is the aperture size, L is the distance between the aperture and the screen, and lambda is the wavelength of light. Applications of Fresnel diffraction are in optical instruments and holography and imaging. The diagram of Fresnel diffraction typically includes a light source, a finite distance aperture or obstacle, and a curved wavefront approaching the aperture. The diffraction pattern on the screen is complex, showing fringes that vary with distance, representing how the curved wavefront interferes after passing through the aperture or around the obstacle. When light encounters a straight edge, such as a knife or a razor blade, the wave bends around the edge, creating a diffraction pattern. This pattern results from the interference of the light waves that bend around the obstacle and the straight edge itself. Key features include light bending and diffraction patterns. As the light bends around the edge, the waves interfere, resulting in a series of fringes. Close to the edge, the fringes are more intense and spread out, and as you move farther from the edge, the fringes become closer together and less intense. This behavior can be explained using Huygens' principle, which states that every point on a wavefront acts as a source of secondary wavelets. These wavelets from different parts of the wavefront interfere with each other, producing the observed diffraction pattern. Fraunhofer diffraction occurs when both the light source and the screen are far from the diffracting object, producing a pattern of parallel wavefronts, plane waves. When this type of diffraction happens due to multiple slits, typically slits, the phenomenon is called diffraction grating. A diffraction grating consists of many slits spaced at regular intervals. Key features are multiple slits and interference, and principal maxima and minima. The condition for constructive interference, bright fringes, is given by this expression, where d is the distance between adjacent slits, grating spacing. Theta is the angle of diffraction. M is the order of the diffraction maxima, and lambda is the wavelength of the light. Diffraction grating pattern. The interference pattern produced by a diffraction grating consists of a series of sharp, bright lines, maxima, separated by dark regions, minima. These bright lines are much narrower and more sharply defined than in the case of double-slit diffraction. The more slits the grating has, the sharper and more intense the maxima become. The diagram for Fraunhofer diffraction due to n slits would show parallel light rays passing through multiple slits. The diffraction pattern on the screen would depict bright and dark fringes, with the principal maxima being significantly brighter and more concentrated than the minima. A diffraction grating is an optical device made up of a large number of closely spaced slits or grooves. When light passes through these slits, it diffracts and interferes to produce a pattern of bright and dark fringes. This device is widely used to separate light into its component wavelengths, similar to how a prism works, but with much greater precision and sharper spectral lines. How a diffraction grating works. The grating has a number of slits per unit length. As light passes through these slits, each slit acts as a new source of light, producing secondary wave fronts that spread out, diffraction. These diffracted waves interfere constructively and destructively, creating an interference pattern of bright fringes, maxima, and dark regions, minima, on a screen. The condition for constructive interference, bright fringes, is given by this expression, where d is the distance between adjacent slits, grating spacing. Theta is the angle of diffraction. M is the order of the diffraction maxima, and lambda is the wavelength of the light. Key features are sharp and well-defined maxima and spectral separation. Types of diffraction gratings include transmission grating and reflection grating. It finds in applications in spectroscopy and optical instruments. Absent spectra, also known as missing orders, occur in diffraction gratings when certain diffraction orders are missing from the observed pattern. These missing orders arise due to the specific arrangement and spacing of the slits in the grating. Why absent spectra occur? Absent spectra occur when certain diffraction orders that would otherwise satisfy the condition for maxima, constructive interference, are cancelled out by destructive interference between the light waves from adjacent slits. This happens when the interference from the slits leads to a zero intensity at specific angles where, theoretically, a bright fringe should appear. Essentially, the diffraction grating's geometry prevents these orders from forming visible maxima. Conditions for missing orders. Missing orders are more common in reflection gratings with wide slits, where some orders of diffraction interfere destructively and thus do not appear. The condition for missing spectra, or absent orders, is tied to the ratio of slit width to grating spacing. If the slit width is large enough compared to the separation between slits, some higher-order maxima overlap with minima from individual slit diffraction, canceling the order. For example, if the slit width is such that the first diffraction minimum coincides with the second-order maximum, that order will be missing from the spectrum. Practical implication is particularly in spectroscopy. The dispersive power of a diffraction grating refers to its ability to separate or disperse different wavelengths of light. In other words, it quantifies how effectively the grating can distinguish between light of different colors or wavelengths. The greater the dispersive power, the more spread out the spectrum will be for a given range of wavelengths. The dispersive power d of a grating is defined as the rate of change of the angle of diffraction theta with respect to the wavelength lambda. This tells us how much the angle of diffraction changes for a small change in wavelength, which indicates the separation of spectral lines. The angle of diffraction for a grating is given by this expression, where d is the distance between adjacent slits, grating spacing. Theta is the angle of diffraction, M is the order of the diffraction, and lambda is the wavelength of the light. By differentiating the equation with respect to lambda, we get d equals m divided by d cosine theta, where m is the diffraction order, higher dispersion. D is the slit separation. Theta is the angle of diffraction. Key features are higher order, m. The dispersive power increases with the diffraction order, meaning that higher order maxima will have more spread out spectral lines. Smaller grating spacing d, smaller slit spacing, or more slits per unit length, increases dispersive power. This is why gratings with very fine lines can separate wavelengths more effectively. Application of dispersive power is in spectroscopy and spectrometers. The resolving power of an optical device, like a prism or a diffraction grating, describes its ability to distinguish between two closely spaced wavelengths. A high resolving power means the device can separate two wavelengths that are very close to each other, resulting in more precise spectral analysis. In the case of a prism, the resolving power depends on how well the prism can separate different wavelengths of light based on the refractive index of the material. The resolving power, R of a prism, is given by R equals lambda divided by delta lambda, where lambda is the wavelength of light being analyzed, and delta lambda is the smallest difference in wavelength that can be distinguished. Key factors influencing prism resolving power are material's refractive index. The prism's ability to disperse light into its component wavelengths is a function of the material's refractive index. Higher dispersion means better resolving power. Base angle of the prism. A larger base angle can improve the resolving power as it increases the angular separation between different wavelengths. Prism length. Longer prisms can provide more dispersion, hence improving resolving power. In general, a prism's resolving power is limited compared to diffraction gratings, especially for high-precision applications. The resolving power of a diffraction grating is the measure of its ability to separate two closely spaced wavelengths. It depends on the number of slits and the diffraction order. The resolving power, R of a prism, is given by R equals lambda divided by delta lambda, which is equal to m(n), where lambda is the wavelength of light being analyzed, and delta lambda is the smallest difference in wavelength that can be distinguished. M is the order of the diffraction. Higher orders improve resolving power. N is the total number of slits illuminated by the light. Key features. Higher order. The resolving power increases with the diffraction order. M. A higher order diffraction results in better separation of closely spaced spectral lines. Number of slits. The more slits in the grating, the higher the resolving power. A greater number of slits means more wavefronts interfere, leading to sharper and more distinct maxima. Comparison to a prism. A diffraction grating generally has a much higher resolving power compared to a prism, especially for high-order diffraction. This makes grating superior for applications requiring precise wavelength discrimination, such as in high-resolution spectroscopy. Wrap up for today. See you in the next video. Do like and subscribe.